All right, guys, today we are learning about even and odd functions. And the way we determine even and odd functions is about the symmetry. So these are the types of symmetries you'll see. When I say symmetry, I mean we can fold the graph and the halves will match. If you fold it, it'll be on top of each other. So if you had this on a piece of paper, if you had this first graph on a piece of paper and you fold it across the x-axis, you see how this half will be on top of that half? That means they are symmetrical. What axis are they symmetrical about? Yep, they're symmetrical about the x-axis. And what about this one?
The Y.
The y. If you fold it down the y-axis, they will be on top of each other. Okay? So the x-axis and the y-axis are common axis of symmetry, lines of symmetry. Now, the third symmetry that you will see is if the graph remains unchanged when you rotate it 180 degrees, meaning this, if you rotate it 180 degrees, it'll be right here, facing down. You see how it's right on top of the other line? And let me do this in a different color. If this one down here, if you rotate it 180 degrees, it'll be looking like that. And it looks exactly the same. So if it remains unchanged when you rotate the graph, that means it'll be symmetrical about the origin. So the origin is a common point of symmetry as well. So those are the three types of symmetries you'll see: x-axis, y-axis, and the origin. Okay, so let's do some tests for symmetry. You can do a graphing test. So let's look at what we already have. Let's say I have a point right here on this line, and I'm just going to make it up. I'm going to say this is at 3, 1. What is this point right here? Yep, 3, -1. So guys, the x value stayed the same, but you see how the y values became negative? Okay, so whenever it is symmetrical across the x-axis, that means the point xy will also have the point x -y. The graph will have xy and x equals or x -y on the same graph. Okay, let's talk about when you reflect across the y-axis, when it's symmetrical across the y. So let's look here. Let's say I have this point. I'm going to call it 3, 3, I guess. Actually, no, I'll call it 3, 4. So we can distinguish. What would this one be?
-3.
Yep, -3, 4. So the y value stayed the same, but the x values became negative. So that means if you have xy and it's symmetrical across y-axis, it'll be -xy. Both of those points will be on the graph. xy will be on the graph, and so will -xy be on the graph. Okay, now let's look at the origin. So that's this example here. Let's say that this point is 1, 4. What is this point? Yep, -1, -4. So the x value changed to being negative and the y value changed to negative. And that is true about every point. Say this point right here is a half and a 2, perhaps. That means this one would be -1/2 and -2. So when it is symmetrical across the origin, when the origin is the symmetrical point, that means you'll also have -x and -y on the graph as well. Okay, so the algebraic test for when it's the x-axis, you'll replace y with a -y. And it'll result in equivalent equations. Here, when you replace an x with a -x, you'll get equivalent equations. And replacing x with a -x and y with the -y. And we'll look at an example of what this looks like. Okay. All right, and you guys should all have this written down. Let's look at the next slide. Okay. So right here, we're going to use a graph to determine if the relation is symmetrical to the x-axis, y-axis, or the origin. Okay, and we're going to confirm our answer algebraically. Okay, so let's look at our last slide back here. We said it is symmetrical about the x-axis if you replace y with negative y, and you still have the same equation. Okay, so let's test that and see. Okay. So if I replace this y, because remember f of x is just y. If I replace it with just a negative y and I still have the same equation, that means it is symmetrical about the x-axis. So let's see if that's true or not. How do I get this y by itself? I don't want a negative. Yep, I'll divide by a negative 1. And let's see what we get. Y equals negative 3x squared minus 1. Is this the same problem? No. Okay, so it's not reflecting, it's not going to be symmetrical about the x-axis, which makes sense, right? Because guys, this is a quadratic and it's positive, so it should look something like that. It's not on its side. So I know it's not going to reflect across the x-axis, and we just proved it algebraically. Okay, let's see the test for the y-axis. So let's go back. The test for the y-axis is replacing x with a negative x and see if you get the same problem. Okay, so let's try that. Let's see if it reflects across the x-axis. So I'm going to clear this off. And let's do the test for the y-axis. So it says replace x with a negative x. So I'm going to replace these with a negative x. Everywhere that I see an x, I'm going to replace it with a negative x. Okay. Now, if we get the same problem, that means it reflects across the y-axis, according to our rule. Okay, so what is negative x times negative x? Yep, it'll be positive now, right? Okay, a negative times a negative is positive, so that just becomes x squared. And then I have a 3, and then a plus 1. Is that the same problem we had? Yeah. So that means, let's look back at our notes. Whenever you exchanged, when you replaced x with a negative x, and it results in equivalent equations, that means it reflects across the y-axis, which makes sense. Okay, so this is y-axis. Okay, let's try the next one. Do we know what this one looks like, kind of, when it's an odd? It's going to look something like that. Okay, so my guess is going to be origin, because it matches the picture in our notes, right? It's probably going to be this one. Okay, so let's go ahead and test it algebraically. So the test to see if it is indeed symmetrical about the origin is to replace the x with the negative x and replace the y with the negative y, right down here. So let's see if it is symmetrical about the origin. All right, so let's test it. Our problem is we're going to put a negative y equals, I'm going to plug in negative x's here. So I'll plug in a negative x and a negative x. Okay, so let's think real quick. I have a negative number multiplied by itself 3 times. So that's negative x times negative x times negative x. What's a negative and a negative? Okay, so this is a positive, right? Times another negative. Okay, so that becomes negative. So anything to an odd power, if it's negative, it'll remain negative. Just remember that fact. So this will be a negative 2x cubed, and positive and negative. So this will be negative 3x. And we have negative y. Let's bring that down. Okay, now I don't want negative y. How do I get rid of that negative? Yep, so I'm just gonna divide all by -1. So I'm gonna get 2x cubed. -1 and a -3, this will be a positive 3x. Did I get what I started with? Yes, so when I replaced x and y with a -x and a -y, we got the same answer. So that means it reflects, or not reflects, it's symmetrical about the origin. All right, so that's how we do those tests. Let's move on to the next set of notes right here. Okay, so let's talk about even and odd functions. A function is even if it is symmetric with respect to the y-axis, which makes sense, remember? Because this is what an even one would look like, and it folds across the y-axis. So that makes sense. And a function is odd if it is symmetric with respect to the origin, right? The parent function of a odd degree polynomial looks like that. And if you rotate this around, this comes here, it'll look exactly the same. Okay? All right, now let's give you the algebra check. The algebra check for this is if you plug in a negative x and you get the original problem, then we're good. And to determine if it's odd, plug in a negative, and if you get negative f of x, then you're good. It's odd. And we'll do an example of this. Okay. So let's do an example. I'll do number 7. Okay, so I'm going to determine, well, I see that it's odd, but let's see what happens. Let's see what we get, because you can't just look at that and tell. So let's do the test. I'm going to plug in, everywhere I see an x, I put parentheses. I'm going to plug in a negative x. Okay, we're doing this part of the test where you plug in a negative x. And let's see what we get. Let's see what we get. Okay, what is a negative multiplied by itself 3 times? Negative. It's negative. Write this off to the side, guys. A negative number, or just a negative, raised to an odd power will remain negative, okay? And a negative number raised to an even power is positive, okay? Just remember that. Okay, so we have a negative raised to an odd power, so this will remain negative. And then a negative and a negative makes this positive. So this is my answer. F of negative x is that. Okay. Did it remain f of x? Did it remain like the original problem? No. Okay, so I'm guessing it's odd because look, if you plug in a negative x and it becomes the opposite, then that means it's odd. So do you guys see how negative x cubed is the opposite of x cubed? Positive x is the opposite of negative x. So when you plug in a negative x and you get the opposite, that means it's odd. Yes. All right, so what we're going to write here is that it is odd and that it is symmetrical about the origin. Okay, let's do number 8. We're going to have the same test. And we are going to plug in a negative x. Plug in a negative x. Okay, I have a negative raised to an even power. So what is it? It's positive, but then there's a negative in front. And then I have a plus 6. Okay, guys, did this remain the same? So is it even or odd? It's even. If it remains the same, it is even. If you plug in negative f of x and you just get regular f of x, it didn't change, it's even. And that means the symmetry is the y-axis. The line of symmetry is the y-axis. Okay, now let me show you guys an example where it's going to be neither. So let's try, I can't remember the answers. Let's try number 11. Actually, let's try number 9. Okay. So we're going to plug in a negative. So I'm going to fill in all these parentheses with negative x's. We're plugging in negative x's. Okay, I have a negative to an odd power, so it is negative x cubed. I have a negative to an even power, so it is positive, right? But there's a minus in front, so we got to bring down that minus sign. And then I have a negative and a negative. That will be a positive 2x. Okay, did I get the exact same problem up here? So it's not even. Is it the perfect opposite? No, what was the problem? Yes, so let me highlight the issue here. The issue is right here. This is a negative x squared and this is a negative x squared. They're not opposites of each other. So it's not odd either. It's neither. That's why we got to check. So this one is neither. Okay. So I'm going to pause it here. I'm going to have you guys do number 10, 11, and 12. And when I say it has to be opposite in order to be odd, for number 11, that includes the 5 too. So if you get everything else is opposite, but the 5 isn't, you still have a plus 5. That is not odd. Everything has to be opposite, including the constant. Okay? Okay, so for this example, again, guys, we're going to substitute these x's with a negative x. Negative x here and a negative x here. A negative multiplied by another negative is what? Positive. So whenever it's raised to an even power, it's going to be positive. So that means this is 10 plus 3x squared. And it stayed the same, didn't it? That means it's even and it's symmetrical about the y-axis. Now, a mistake that I walked around and saw, not only in this class, but the last class, is people made this plus sign a minus sign. I'm not sure. Oh, I'm not sure if it's because they forgot that this makes it positive, so it remains positive, or if they think that whenever you replace this, you put the negative here and not inside. I'm not sure what the misconception was. But do you guys see the right way to do it? Okay. All right. Did you guys finish 11 and 12? Yes? All right, nice. I'm going to stop here. We're almost done. Okay, so guys, just repeating. If you have an even power, or I'm sorry, it'll be symmetrical across the y-axis. And if it's an odd power, then it is symmetrical I'm gonna say the point of symmetry is the origin. Okay, write it like that. The point of symmetry is the origin. Symmetry. Sorry, that's sloppy. We're just repeating our notes here. Okay, now guys, last unit, we talked about end behavior. We talked about end behavior. So guys, looking at this graph here, this is a even power. Whenever you have an even power, your graph is going to look like this. If you have an even power, but there's a negative in the very front, it's going to face down. Okay, so let's talk about the end behavior. Last week, we said as x goes to negative infinity, what happens to the y? As you go this way, what's happening? It goes to infinity. And as x goes to the positive side, so as we travel this way, what's happening to the y's? It's also going to infinity. So guys, that's how you write the end behavior. So guys, go ahead and finish these 4. This is a review for you. And I'm going to stop it here. We're officially done with the notes.